Hey everybody, it's Dr. Wood, and today I want to talk about hypothesis testing with you. Some of you have already come up with your hypothesis for your paper there, but I want to talk a little bit about some of the pitfalls you may run into with hypothesis testing and some of the research you're going to be looking at, specifically some of the primary literature you're going to be pulling from. So again, what is our hypothesis? Remember, this is something that is developed a priori. It's not going to be influenced by the results of a study. There's basically what you think you're going to find prior to going into the study. So for instance, when I did my coral snake research, it was about either delaying antivenom or giving it right away for every bite that came in. My a priori hypothesis said people should wait because they won't do any worse, right? That could have been totally proven wrong, and the null hypothesis may not have been rejected, or it could have been bore out and I reject the null hypothesis, right? Again, it's always make sure that you consider what your null hypothesis is as compared to your actual hypothesis. And again, it may not always be as clear cut as well. Okay, they're both the same. It may not always be the case there. And so again, when you reject that null hypothesis, that meaning that you did find a statistically significant difference between the groups. Now, the difference may be so small that clinically it makes zero difference whatsoever to you from actually taking care of patient standpoint, but statistically you did find something there, right? If you're failing to reject the null hypothesis, that doesn't mean there's no difference there, right? So that's a really important thing that you'll find when you're looking through the literature. Just because they don't find any sort of positive results, that nothing is statistically significant does not mean that there's no difference. It just means they couldn't find it. So why couldn't they find it? Well, frequently it has to do with issues of power, which we'll talk about in just a second here. But if you recall from EpiBio, we talked about different types of errors that can occur here, right? So here we're going to have our null hypothesis, which is true in this case, meaning there's no difference between the groups. And here we have our null hypothesis is false. And this is saying that there is a difference between groups, right? So this may be our actual hypothesis here. And this is the two different decisions. We can either reject it or not. Now, if the null hypothesis is true and we reject it, that we're saying that there is a difference when one's not there, that's a type 1 error, right? It's a false positive error. That's the one you don't want to be making. It's more deleterious because you're saying, look at these results. There is a difference here, but it actually didn't exist. You don't want to do that, right? We'll talk about some ways to correct for that in just a little bit, ways to minimize the risk of making that sort of error. On the other hand, though, if you have a false null hypothesis, meaning there is a difference between groups, and you fail to reject it, that's a type 2 error. These are fairly common, and this is going to be the ones I was talking about before as being issues of power. And remember, power is going to be pretty much directly influenced by the number of patients you have involved in your study. So, power and sample size. Remember that basically the more people you have in your study, the more power you have to find a difference, okay? So a study with 3,000 people are going to be much more easy to find a true difference between them if one exists than if you had 30 patients, okay? Problem is, it's hard to do studies with a large number of patients. It's resource intensive, you may not have funding to do that, and so you'll find a lot of your studies may include 25 people. Not going to be as strong or as much power to find a difference as if it included 2,500 people, right? So frequently what researchers will do is that they will do power calculations a priori, meaning before the actual study is performed, they're going to go ahead and do power calculations to try to determine how big of a sample size they need, how many people they need to show a given difference between the two groups, okay? Again, there's more details to it than that, but basically that's what it's trying to figure out. How many people do we need in our study? How much recruitment do we need to do to meet those numbers, right? Most studies end up being underpowered, though, because again, it's hard to do it, right? So it's difficult to get patients to come into studies, or especially if you're dealing with things that are relatively rare, that can be a problem too. So if it's a disease that only affects 50 people a year, that's hard to recruit for versus something like diabetes, which millions of people have, right? And so you'll find this, and this is a good thing to look at too, is power calculations and sample size really should be addressed in the paper. So they need to be able to address the fact that, hey, if they didn't find any results, any positive results, they found that there's no difference, and they could not reject the null hypothesis, they need to be able to say, like, well, maybe our sample size was too small, maybe our study was underpowered, and that's a really frequent cop. That's a really easy thing to say. If you don't find anything, you're like, well, we just didn't have enough people to find it, right? And that's totally reasonable criticism of their own paper. You'll find that quite frequently. I mentioned convenience sampling here too. Remember, this is just like things that are just coming through the door. So for instance, in the ethics talk, I mentioned about doing a study with different types of antivenom. That's definitely convenient sampling, because I can't go and purposefully envenomate people with pit viper bites. I had to wait for them to come to us, right, in the ER. So for instance, if it's the summertime, you're going to get more snake bites than if it's the winter time. Or if we don't have anyone to actually run the study, there's no study coordinators working in the middle of the night when some of these bites come in, then that person can't be included in the study, for instance. So again, sample size is difficult. Getting enough people to actually power your study can be pretty difficult. You'll find this to be a frequent criticism of a lot of papers you're going to find. So next thing I want to mention here is multiple comparisons. The reason why I have this blind squirrel here is because he has found his nut, meaning that you can make a gazillion different comparisons and eventually you're going to find something. I'm sure you all remember when we talked about this before. Remember that when you say, my comparison achieves significance at a p less than 0.05, remember that 0.05 is still 1 in 20 chance of finding something significant, right? So it's a 5% chance to say there's a difference here when one actually isn't. So it's not great, right? You don't want to say like, well, there's a 1 in 20% chance that you're going to die. I'd rather hear I have a 1 in 1,000 chance I'm going to die, or something like that. I guess it's a 1 in 1 chance I'm going to die. We all are at some point, right? But you get what I'm trying to say. All these comparisons should be done a priori as well. So a person, when they're going into a study, they should know every single comparison they're going to make before they collect any data, because the problem is that they start to just make up stuff as they go along or try to come up with things. Say they do their analyses and they don't find anything, right? So they're like, great, I just wasted all this time, all this money. Let's just start making more comparisons. Let's try looking at it this way. Let's look at it this way. Let's look at it this way. That's the multiple comparisons problem. Eventually you're going to find something, and that may be one of those type 1 errors where you make, you say, I'm going to reject the null hypothesis when you really should not have, because there was no difference, okay? Now remember, there's ways to correct for this. The most common one is that Bonferroni correction, where basically you take that 0.05 and you just divide it out by how many other comparisons you're going to make. So for instance, if I'm going to make 10 comparisons, I take that 0.05 and divide it by 10. So now all of a sudden, each of my p-values has to be less than 0.005, for instance. If you see a Bonferroni correction, that's what they're trying to do. They're trying to account for the fact they have multiple comparisons, and thus they're making it more difficult to achieve significance, so that way they're less likely to make a type 1 error or a false positive error, as you know. So those are big things to look at, because again, and I'll never forget, I had one student who was learning about multiple comparisons for the first time, and she was like, wow, I remember I was in my biology lab, or I was working with a biology professor in college, and we were working with these zebrafish, and we were trying to find some kind of difference, and we just couldn't find anything. And so he said, just keep comparing different things until you find something significant. And she just had this look of like, oh my gosh, that was like totally off. And I was like, exactly, right? Because people don't like to publish negative results. It's less likely to get published. It's a big problem in a lot of the medical literature that's out there. So just something to think about. Anyway, so that's it for the end of this topic. If you have any questions, though, certainly let me know, and I'll talk to you soon. Thanks a lot. Bye.